We have all been mistaken about black holes, because if we calculate using pure physics, a black hole is not the ultimate end of everything, it is a power generator. In fact, any sufficiently advanced civilization that lasts long enough will eventually have to utilize black holes for energy. Hearing this, you might want to argue, don't we have the sun's energy to use? The crucial point lies precisely in having a sun. So next, let's not look at black holes yet. Instead, let's clarify the energy limits of relying on stars. Before discussing how advanced civilizations might use black holes, first we must admit one thing: relying on starlight will eventually be insufficient, because stars appear bright, but they are remarkably inefficient as engines. Take our sun for example. The proportion of its mass converted into energy is only about 0.7%. Where does the rest go? Mostly dissipated as waste heat, light, and various losses. For a young civilization, this is certainly enough. But once you stretch the timeline to billions of years, the problem suddenly becomes stark. Stars run on hydrogen fusion, and hydrogen is finite. The result is simple: stars will exhaust their fuel age and fade away. You can live off them for a while, but if you depend on them for a very long time, you will eventually hit a fuel limit. Is there a more drastic path? Indeed there is. Gravity is different. Gravity does not burn out or shut down. It just keeps pulling. And precisely because it keeps pulling, any object with gravitational potential represents usable energy. So when we search for the ultimate power source, we should not fixate on a quietly shining star. We should target something that locks energy into a gravitational structure like a black hole. But there is a catch: not just any black hole will do. A stationary black hole is more like a simple drain, offering little stable, sustainable output. What we really need is a spinning black hole, a Kerr black hole. Spin means it stores energy in its rotation, energy that can theoretically be extracted and theoretically be tapped. Why does it spin? In the violent birth of a singularity, a collapsing star rarely falls straight in. It usually twists and spirals down. Conservation of angular momentum compresses the spin, making it fast enough to boggle the mind. More crucially, this is not merely a sphere rotating, it is spacetime itself twisted into a vortex. Think of it as a colossal flywheel. The faster the flywheel spins, the more kinetic energy it stores. A spinning black hole is the ultimate flywheel. It locks the rotational energy of a dead star inside a gravitational cage. Now here is the key point. If you examine the energy budget of a spinning black hole, you find something counterintuitive. Not all its mass energy is locked forever behind the event horizon. A significant portion is tied to its rotation, accessible and extractable. Up to 29% in theory. This means, of a spinning black hole's total mass energy, even if you capture just a fraction, the amount could surpass the total output of a sun over its entire lifetime. So ultimately, we need not an ordinary power plant, but a power station orbiting a black hole. Future engineers looking at the night sky would see darkness not as emptiness but as an untapped energy field. Black holes would no longer be predators to avoid, but a resource, a harvestable source of power. But recognizing it as a battery is one thing, actually plugging into it is another. Stars give off energy. You can catch it with a solar panel. A black hole does the opposite: it pulls energy inward, holding it tightly. To take it you must intervene and make an exchange, yet you cannot touch the event horizon itself. That is forbidden territory. Enter and you never return. So the only viable region for work is just outside the event horizon, right next to it. With a spinning black hole, this region includes an extra boundary, forming a special shell called the ergosphere. The name is literal, not metaphorical. This is where work can be done. Because of frame dragging, the black hole drags the surrounding spacetime with it. The result is that standing still in the ergosphere is nearly impossible, not faster than light, but rather trying to remain stationary relative to the distant universe. Cannot be done here. You are forced to rotate with it. It is within this turbulent workspace that the Penrose process becomes possible. The concept is elegant, but the method is counterintuitive. You send a parcel of matter into the ergosphere, moving with the black hole's spin. Then, at a precisely calculated moment, split it in two. The first half is sacrificed, kicked backward against the spin direction. It falls past the event horizon and is lost forever. The second half is hurled forward by the reaction, shooting out of the ergosphere, escaping the black hole's grip. The real energy extraction happens here, because the ergosphere's spacetime is special. The sacrificed backward falling piece can enter a negative energy state. When the black hole swallows it, it does not gain energy, it effectively consumes a negative. The result is clear: the black hole loses some mass and spin. In other words, we fed the black hole a poison pill with the sacrifice, slowing its rotation. Meanwhile, the escaping half leaves with more energy than it arrived with. Where does the extra energy come from? It is the difference extracted from the black hole's spin. Once it escapes, it can be captured farther out by a ring-shaped collector or magnetic coil system, converting its momentum step by step into electricity to power an entire civilization. In short, you trade a piece of waste for a massive amount of usable power. But throwing things in and splitting them is ultimately too crude. For a civilization at the Kardashev Type 2 scale, industrialization must upgrade from mechanical to electromagnetic. This leads to super-radiant scattering. Think of it as the concept behind a black hole bomb. You surround a spinning black hole with a giant spherical mirror, a massive reflective shell, then fire electromagnetic waves into the ergosphere. The waves enter the twisted spacetime and scatter back slightly amplified. The mirror is key. It reflects the stronger wave back in, so it goes in again, scatters and grows stronger once more. Thus, energy bounces between the black hole and the mirror, building up each time, a positive feedback loop, growing exponentially with each pass. Now the engineering challenge boils down to one word: containment. You are building a cosmic-scale laser cavity. The mirror must have controlled openings and valves to release energy in a steady stream, as a directed beam. Otherwise, energy density inside the cavity keeps rising, until it either tears the megastructure apart, or more extremely, the light becomes so dense it creates its own gravity, collapsing into a new black hole, a Kugelblitz black hole. So you are generating power with a black hole, while risking the creation of another one. But if you can stabilize it, the payoff is staggering. Earth's most promising nuclear fusion converts less than 1% of mass to energy. Running the Penrose process on a rapidly spinning black hole can theoretically reach 29%. This is nearly the most powerful engine physics allows. You simply need to keep feeding it matter for trade, keeping the negative energy transaction going, or keep amplifying electromagnetic waves via superradiance in the cavity. And this engine can run almost indefinitely. So this is more than a big power plant. It is a watershed in the history of civilization. We currently have a stellar economy. We take what the sun gives, essentially passive scavenging. But once you can cultivate a black hole, energy scarcity begins to lose its meaning. Planetary terraforming, interstellar arcs, megastructures, these become questions of how, not if. Questions of logistics, allocation, and focusing resources on the most critical steps. An even more profound value lies not in power but in longevity. We live in the stellar era now. The universe is like a bright summer, full of light and warmth. But summer will end. In the deeper future, star formation will dwindle, eventually reaching zero. Stars will age one by one and fade away. The universe will enter a long winter with only the cooling embers of dead stars. A civilization reliant on solar power would essentially be disconnected. Black hole energy is not produced by burning fuel. It comes from gravitational structure and spin. As long as the spin continues, you can extract energy from it. And this spin is incredibly stable. It can persist for trillions of years. So for a black hole farmer, that future is not an end, just a change of seasons. Maintaining a heated oasis during the cosmic freeze, giving civilization a continuous energy source, even in the coldest epoch. They would gather warmth from the singularity's spin, like travelers keeping the last fire burning in endless darkness. By that time, civilization likely won't reside on planets. Planets would become frozen tombs, struggling to maintain liquid water. They would more likely live in the safe zone beyond the ergosphere, in orbital swarms, in rings of artificial habitats. Those habitats would float, seemingly far from the black hole, but connected by an invisible energy conduit to the dark engine below. Thus their identity would completely change. They would no longer be gatherers of starlight, but tenders of spin. Not waiting for a sun to shine, but guarding the last sustainable light in the cosmos. So in this narrative, the black hole is re-evaluated. It is not just a devourer but could be a lifeboat. It forces us to reconsider the meaning of darkness. We often see the unknown as monstrous, but physics hints at something more poignant. Life's final path might lie not in the light but in the deepest shadow. We study black holes not just to power machines, but perhaps to let the flame of consciousness outlive the stars and endure beyond the aging of the universe.